All right, well, we are here with Henry Spencer. Thank you very much for joining us today. So you have given talks at the Space Access Conference for a couple of years now, talking about asteroids, what we know, what we don't know, and what their threat is. So can you tell us a little bit more of what your perspectives and different things that you've been noticing over the years on the knowledge that we've been gaining on asteroids?
Well, things have been picking up a fair bit because we've been getting more spacecraft visits to asteroids. We've been getting more direct information as opposed to guesses and inferences made from long distance. And that's been turning up some puzzles and some uncertainties. There's probably going to be more of that. These are very diverse bodies. There's a lot of differences between the different asteroids, many of them not very well understood. The idea that that there were only a few classes of these things, that you could classify them quite well by studying them by spectroscopy from afar, is looking increasingly ridiculous. There's a lot of diversity there that we don't understand. Probably a lot of surprises lurking once we start investigating them in more detail.
As of right now, with the spacecraft that we have been able to send, both the United States and countries all over the world, what sort of information or what sort of methods have we been able to identify these different classes and now new classes of asteroids?
Well, most of the asteroid encounters so far have been just flybys, spacecraft that were on their way to something else and managed to make an asteroid flyby or two meanwhile. And you don't actually learn a lot from flybys. You can get some pictures, which gives you some idea of what the terrain is like on one side of the asteroid, because the other side is in darkness. And you may not even get a full view of the one that's lit, depending on the path the spacecraft is following. You might get some data from other instruments, or you might not. If it's a big asteroid, you might learn how heavy it is by measuring how much it deflects the spacecraft's path. If it's a small one, there's not enough deflection, you can't tell. So very, very basic, very sketchy information. For details, you really want to at least be in orbit around the asteroid, and that's only been done a couple of times. That's harder. It means you have to match velocities with the asteroid. But then you can study it at length, see it from different angles, wait for it to rotate so more of it is in sunlight, study its gravitational field by how well the spacecraft orbits and what corrections need to be made to keep it in orbit. Study it with instruments like magnetometers and radar instruments and things like this, which have to be close for long periods of time to get results. Still more ambitiously, you can land on the asteroid to the extent that it means much to land on something that has hardly any gravity. You can try to get samples from it and bring them back, and so far that's been done just once. The Japanese Hayabusa mission, which had almost everything go wrong, and some very impressive work by the ground controllers managed to bring it limping home with a few particles of dust in its sample container from asteroid Itokawa. And that alone actually resolved one major puzzle that had been bugging people for a long time about the relationship between asteroids and meteorites.
And what was that?
Well, a large fraction of the meteorites that fall to Earth are in a category called ordinary chondrites. A large fraction of the asteroids near Earth and in the inner asteroid belt are called type S from their infrared spectrum. It was tempting to say, okay, the ordinary chondrites must come from the type S asteroids. The trouble was that the infrared spectra didn't match. Lab spectra, take an ordinary chondrite meteorite, run a spectrum of it in the lab, compare it to the spectrum you get off a type S asteroid, they're not the same. There were very few asteroids which actually had spectrum that looked right for ordinary chondrites. The speculation was that this is what was dubbed space weathering. That if you put an ordinary chondrite surface out in space for a few million years, exposed to sunlight and radiation, maybe cosmic rays as well, then you would get something that looked like a type S spectrum. And it was a plausible guess, but nobody really knew. And now we know, because those particles from Itokawa are definitely ordinary chondrite material, and their surfaces do indeed have alterations, probably from solar radiation, that give them a spectrum like the class S spectrum.
Interesting. But in the lab settings with the meteorites that had already hit, they weren't able to detect that at first.
They weren't able to duplicate anything. The meteorites by and large haven't spent a lot of time in space by themselves. They're chips off bigger bodies. They haven't been out on their own for very long. And they've had some of their surface burned off by coming in through the atmosphere. So there was never any definite confirmation of this. And now there finally is, but it was a close thing. Hayabusa was almost a failure, quite a number of times actually.